My name is Rob Webb. I am the Sales Enablement Manager with IDS. And yes, as Peter says, we'll be talking to you today about event-based cameras and imaging and how these fit in with high-speed imaging. So at IDS, we've got a broad range of cameras with different interfaces, including USB 3 and 10 gig E, offering frame rates in the sort of hundreds to thousands of frames per second, but at lower resolution. So in reality, if I'm honest, we can't really truly hold a flame to my fellow presenters here in terms of high-speed frame-based technology. So when we were invited to speak at this seminar, our thoughts kind of turned to alternative approaches, and this is where event-based imaging came up. So the benefits of high frame rates are clear. A higher temporal resolution means we get more information to either track or count objects or detect objects. And ultimately, this means we have more accuracy with our results. With traditional frame-based high-speed imaging, this tends to be a more expensive technology and can generate extremely large amounts of data. And this requires either on-camera storage or high-bandwidth data interfaces. And if the application calls for a compromise on costs or the amount of data generated, we have to normally sacrifice either spatial resolution or temporal resolution. So an alternative approach is event-based imaging. Event-based imaging, which is also known as neuromorphic imaging, is a different approach and is based on how our vision works. Our eyes don't take individual frames. It's more our cells in the eye report changes in the scene to the brain. And if nothing changes, then the cell doesn't report a change. And if something moves, then the cells in the eye report the change, and our brain effectively samples that. When it comes to the data we get from event-based sensors, there is no concept of frames either. We can see here a comparison of a frame-based camera on the left and a 2D rendering of the event-based data on the right. And the key difference we have here is that we're only seeing or only sending data about pixels that have changed in time. And actually, the data isn't delivered and processed in the same way as a standard 2D frame. Instead, we get a continual stream of data containing information about any activated pixels. So this is the XY coordinate of the activated pixel, the polarity, so whether it changed from dark to light or light to dark, and this is where we see the blue or white encoding in the data we see there. And then we also get a timestamp of when the event occurred. And then we can render this into a 2D video, but for true efficient processing and really making the most of event-based data, the data is processed in this XYPT format with specific algorithms. And Prophesee, the manufacturer of the sensor that we have in our cameras, sum it up very nicely, saying independent receptors collecting all the essential information and nothing else. There are a number of advantages to this approach, some generally relevant to machine vision and vision applications, and others more towards the high-speed vision side of things. So we start with the general advantages, and the first thing to note is the event-based sensors that we use have extremely high dynamic range characteristics. So actually, it's a logarithmic response, which means we can achieve dynamic ranges of around 140 or even exceeding 140 dB. With traditional machine vision frame-based sensors, the dynamic range tends to be around 70, 72 dB or thereabouts. So you can see that we have a significant step up in dynamic range. And in pictures, in the example we see here in the left image, we have a standard frame-based image of a car coming towards the camera, and really we don't see very much information other than the glare from the headlights. In the event-based image on the right-hand side, we can see, well, first of all, there's no glare from the headlights, but we start to see more information. And in this case, we can see a pedestrian appearing on the right-hand side. Through the same tests, as the video rolls forward, we can also see that, again, the glare from the headlights is still limiting some of the detail in the frame-based camera. But in the event-based camera, we can even start to see details of the car, things like the car manufacturer and even the license plate. Coupled with the high dynamic range is also very low light sensitivity as well. So this video, we can see on the left-hand side a frame-based camera and looking into the shadows, and we can't really see much going on there. But with the event-based sensor, we can pick up this motion. We can see that there's somebody walking around and then use that to track them through the scene. So the low light sensitivity really gives us a performance boost. As event-based sensors do not have a concept of exposure time, there's also no issues with motion blur. So looking back to the images we saw earlier with the rendered image, we can see it looks like it's blurring, but this is just a 2D representation of the data. We're effectively collecting a number of events over time, which is why we see sort of effective blurring in that image data. But the true data from the camera, there's no concept of motion blur. There's also no concept of global or rolling shutters, so this isn't a selection process that we need to concern ourselves with when selecting the right camera. So those are the general advantages. We can also look at how this fits in with high-speed imaging and sort of some comparison to frame rates. I've already mentioned that we don't have the concept of frames, so frame rate isn't the truly correct comparison, and some people would shiver if I even start talking about frames with this technology. But we can talk about a time base, and this is what we can use to give some comparison. So we have a time base down to 100 microseconds, which gives us an equivalent of around 10,000 frames per second. And the example we see here is a laser scanner using different event accumulation times and rendered at different frame rates. So the accumulation time determines the number of events represented in a single rendered frame. So the longer the accumulation time, the more events we see and the more kind of effective blurring we see. Again, this is just to represent the data in a visual way and demonstrate the ability to capture high-frequency events. The processing of the XYPT data stream with specific algorithms is the most efficient way to process the data, but you could use traditional 2D algorithms in some cases. Coupled with this high sampling frequency is also the point about the data rate. So with frame-based imaging, each pixel is exposed and read out for every single frame, even if, say, 90% of the scene is unchanging. These pixels have to be read out and transferred. So for a megapixel sensor running at a reasonably high frame rate of 1,000 frames per second, at 8 bits per pixel, we're generating a gigabyte of data per second. And this has to be transferred to the host and then either processed or stored, even if most of the data provides no valuable information. With event-based imaging, we're only transferring data from pixels that have detected a contrast change. So if nothing changes, the data rate is extremely low. We can see down to sort of a couple of hundred kilobytes. And even at the peak transfer rates, we're at sort of 130 megabytes per second. We can see again another rendering of this in this video. I'll just jump in and pause it for a second. So if we don't have any movement in the scene at all, we just have a few random events, which are just generated essentially noise, but can be reduced with processing and configuration. But we can see we're only generating sort of around 500, 600 kilobytes of data. Once we start to see some movement in the scene, in this case, a toy car on a turntable, we can see the average data rate then jumps up to about 8 megabytes per second, and we have about 1.5 million events per second. And then later on in the video, if I then start to wave my hand in front of the camera to generate as many events as possible, that's when we can see the data rate start to go over 100 megabytes per second. The event rate sort of over sort of tens of million events. But ultimately, even in the most extreme cases, we have still a low data rate. So this is a much more efficient way to transfer and process data. On top of that, the sensor itself has very low power requirements, and due to the reduced data rates, and our cameras can be based on USB 3, offering a power consumption of just 0.6 watts, 3.4 watts at the peak. And consider also that if the data has to be processed in line, because of the lower data rates, the processing power can be reduced as well, meaning the entire system power budget is much lower. And Similarly, related to the power requirements, the hardware platform is much more compact. So here we see just the sort of standard 29mm cube for an industrial house camera and just 61 grams. And a board level version at just 6.4 millimeters depth and 29 by 29 square and just 5 grams. Both of these without lenses, but if we add just like an S-mount lens, because the sensor is small enough to support S-mount lenses, then it's only adding a few grams and a few millimeters to the overall form factor. So I guess it'd be interesting to see some applications. First of all, we have live tracking. So this is an application for spatter monitoring in welding, where the spatter gives some indication of the quality of the weld. This requires both high speed for the tracking purposes and also a very high dynamic range because of the brightness of the scene. Eye tracking is a very strong area for event-based imaging as well. The speed offers the obvious advantages, more information for more accurate tracking, and the low power requirements of the sensor makes it viable for compact handheld devices for use in remote locations, as well as in lab-based devices. We can think about things like predictive maintenance. It's typical that in machinery components, are periodically replaced to avoid catastrophic failure. All systems are shut down to test and make sure things are functioning okay. But potentially by monitoring vibrations of motors, we can predict or certainly look at the vibrations of the motors. And if we see any unusual frequencies or unreliable frequencies, then we can perhaps predict a failure earlier than a catastrophic failure would let us know. So it's no longer predictive, but more of informed maintenance. And the technology is also used in the food industry and the pharmaceutical industry for real-time counting and gauging. So typically, this is a line scan application looking at products falling through the field of view. With the event-based imaging, it's an easier setup to configure and a lower cost system, and we can provide object counting and sizing as well at high speeds. And similar application looking at ink droplets in flight, seeing how they form through as they fall. Again, typically a line scan application. So with the event-based imaging, we're offering a low complexity and a price advantage as well. And perhaps, a very hot topic at the moment with Homeland Security is drone detection. So we see here on the left-hand side a frame-based image where it's a very noisy scene. It's very difficult to detect where the drone is. But with the event-based image, because all of the noise in the scene is static, it's not generating any events. So when we see the drone moving through the scene, it's very, very clear to pick up. Because of the high speeds, we have low latency, we have high dynamic range. It's an outdoor application, so we have to deal with direct sunlight. It can also be a nighttime application, so low light sensitivity is a benefit here. And the low power requirements offer the ability for it to be remote setups as well. And quite a number of other application areas in things like robotics, autonomous systems, sports analysis, motion capture, and so forth. If you want to get started in this technology, then IDS works in partnership with Prophesee. We've developed a camera based on their IMX686 sensor, and it's available in a housed industrial camera or in the board level cameras for OEMs. We're using a USB 3 interface, and so it's easy to connect to almost any system. And for the optics, we use standard C-mount or S-mount optics, so there's nothing special here. It's calculated in exactly the same way as we would with the standard frame-based camera. And when it comes to the software, Prophesee have a full SDK called MetaVision, which includes the camera control and processing algorithms. And it's supported under Windows and Linux, and there are libraries for C++ and for Python. Since we're not dealing with traditional 2D data, it makes sense to leverage the tools that Prophesee have already developed around the event data stream. And here the algorithms are available for tracking, for flow monitoring, vibration estimation, particle counting, and there's a few more as well. So all you need from IDS is the hardware, the camera, the lens, and a plugin to get the data into the Prophesee MetaVision SDK. And We see this as a very important technology for the future, to the point where we've recently signed a statement of intent to work closer with Prophesee within the event-based imaging world, and we look forward to the advances in this area. So we can summarize then that with event-based imaging, we can achieve high-frequency imaging with unmatched dynamic range, greatly reduced data rates, low power budget, and compact form factors are available in an industrial and board-level camera for OEMs. There's a comprehensive suite of processing algorithms already available for this data, and an ever-growing range of applications as this technology comes to the market, matures, and finds more and more new areas to work in. Thank you very much for your time.